let's talk about the LC circuit. This is a circuit that just has a capacitor and an inductor. There's no battery or resistor or anything else, just those two. And once you close the circuit, then current can flow. So the capacitor is charged to begin with. And as I mentioned, the circuit is closed, so the charge can flow. We can have current passing through the wires. And this is going to happen, of course, because the electrons here repel each other. So they'll be repelled off, and they'll go all the way around to the positive plate. Now, the inductor, however, remember how the inductor behaves. It resists any change in current. So yes, the capacitor is going to push the electrons off, but the inductor is resisting that change in current, which to begin with was 0. So it's resisting that change in current, but the capacitor is going to win. I mean, charge is going to flow all the way around, and indeed the current is going to increase. And what that means is the charge of the capacitor is going to decrease until eventually it goes to 0. And at this moment, the capacitor is done. It's not pushing anymore. But now there's a current in the circuit, and the capacitor isn't pushing anymore. That means the current should start to decrease. In fact, if it weren't for the inductor, it would go to 0 right away. But the inductor is there, and the inductor resists change in current. So now the inductor is going to start behaving like a battery. It's going to keep the current going. And so remember that the electrons were going this way, so it's going to pull electrons off of this neutral plate. It's going to pull more off of them, and that's going to make this plate positively charged, and the other plate's going to become negatively charged until the capacitor gets back to its original charge. And at that moment, the inductor is spent, can't do any more, current stops, and then what happens? It starts all over, but it goes in the other direction. Now the electrons flow this way, they flow around, and this repeats. And it turns out this circuit exhibits simple harmonic motion. And that is a little bit mind-blowing. It's certainly somewhat unexpected, but it means that the period is going to be independent of the amplitude. Now, when we say the amplitude, what are we talking about? Okay, well, let's take a look at the graph. And what I've got here is a charge. This is the charge on the capacitor versus time. Okay. And you can see we're getting that sinusoidal curve. And in fact, the formula here, let me go ahead and write it down. So the charge is a function of time. It's the initial charge times the cosine of omega t. Omega is the angular frequency of this circuit. So when I say this is simple harmonic motion, and remember that the period is independent of the amplitude, so what is the amplitude I'm talking about? It's this. This is the amplitude right here. This is the amplitude. And so what I'm talking about is the charge on the capacitor, the initial charge on the capacitor. It doesn't matter what the initial charge on the capacitor is, as long as it's non-zero. But it's 0.25, it's 0.5, it's 0.4, it's 20. It doesn't matter. The period will not change. That's the idea here. Now, I've already mentioned omega. Let me tell you what that is. The angular frequency for this circuit is 1 over square root of LC. And also remember, from simple harmonic motion, we know that the angular frequency, which is measured in radians per second, is going to be equal to 2 pi times the frequency. The frequency is in hertz. And the only other thing to remember is that the frequency and the period are just reciprocals of each other. So if you multiply them together, you get 1. Okay, now let's talk about the energy. So if we're talking about the energy in the system, so the total energy in this system is going to be a combination of the potential energy of the capacitor plus the potential energy of the inductor. The formula for the capacitor, that's Q squared over 2C plus 1/2 L I squared. So at any moment in time, this statement is true. Now we can look at specific moments in time and get slightly different formulas that come from this. So if we look at the situation where, well, let's just look at this one right here, where there's no charge. So Q is 0. Okay, if there's no charge, that means all the energy is in the inductor, and that must also mean that the current is at its max value. So there we go. We can also look at the situation where there's no current. In other words, when the charge is maximized, and that is, to be more precise, is the initial charge. And so at that moment, all the energy is in the capacitor, and we get Qi squared over 2C. So this is what we saw when we did simple harmonic motion, only there we were dealing with kinetic energy and the potential energy of the spring, when we were, at least when we were doing the spring block system. But here we have the potential energy of the capacitor and the potential energy of the inductor, and we get very similar formulas. We're just talking about different quantities. The last thing I want to mention is the LC circuit has a lot of uses, just a couple that I can name. It's a clock, again, because we're talking about simple harmonic motion. The period is independent of the amplitude, so the period isn't going to change, so you've got a clock. Okay? Just as we saw that a pendulum, the grandfather clock, here you go, that's exhibiting simple harmonic motion when you have small enough oscillations, and so you've got a clock there with the pendulum. Same thing here, except this is always simple harmonic motion. The pendulum was you had to have the amplitude be less than, much less than 1 radian. Another use here for the LC circuit is radio transmitter. You can use these as radio transmitters.